Okay, so we start to the second lecture of the afternoon session. So we are happy to have Professor Mboyo Esole talking us about theory, anomalies, something like that.
Yes.
Okay. Thank you.
Hi everyone. It's a pleasure to give the talk here. So basically to follow on what Komon was talking, at a certain point he mentioned the link between gauge theory and singularities. So this is basically what I'll be talking about. Now my point of view on this has changed, and I can see how it's actually something that studied in mathematics without the physics. But then the physics gives also a beautiful picture of it. So first I've got to introduce what is F theory. And so F theory is a part of string theory where we can actually use a lot of geometry to describe configuration of gauge theories. And so typically, the typical picture would be to think of type 2B. So you start with type 2B string theory. This is in 10 dimensions. And it has all kinds of fields, but in particular, it has scalar fields that you can express as what people call an axial dilaton. So let's go with tau, and it has like a real part and an imaginary part, which is always positive. And so we can express it with an exponential like that. So this is your axial dilaton fields written tau, and very much like what we used to describe, for example, the complex structure of a torus. Okay, so let's say this is one. I have an axis like x and y, and this one here would be tau, and I'm describing, basically identifying both sides of this shape to describe a certain torus. So then I can ask myself, so if I have different tau, which one corresponds to the same shape for this torus? And there is a symmetry that basically preserves the shape with the condition. So here I immediately break to the arithmetic rule that ABCD define an element of SL to Z. And since there is a ratio, you can see that actually the overall sign doesn't matter. So I could move to PSL.
Is on or
I guess it is right.
yeah. Oh, it looks on. So okay.
Yeah, it's really on.
Okay, then
All right. Is it maybe the position of my
single position should
So online people think
one person. I asked.
wow.
I can't think of how. Oh, now it's okay.
It's
Now it's
okay.
okay. Yeah.
Okay, online people, I'm sorry. So okay. So then we move on, and so we have this symmetry, and from type 2B, this is actually the symmetry you expect for that field. So now the question is, when you give a compactification of string theory, you actually have to say what happens to your tau. And one beautiful way to do it is to give the following picture. So you have some base manifold B, and then for each point of your base manifold, you have like a different value of tau. So geometrically, you could represent it in the following way, in which instead of just giving the field tau, you actually first think of it as for every point, we are going to define some torus that will tell us what tau is. And then the beautification of this is to really think of giving a structure in which locally your geometry looks like a base on a torus. And that's the idea of elliptic fibration. So an elliptic fibration basically would be then this map where, let's say you have a total space and you have your base, and basically the fiber is an elliptic curve. So now an elliptic curve is an algebraic curve of genus 1 with a choice of a rational point. And so these objects, they're very ancient. You can describe them thinking about cubic curves in the projected plane. So you can trace the study of such objects like for 1,000 of years, and we use them to secure bank transaction with elliptic cryptography. We use them to understand string theory, gauge theory. So they are like beautiful objects. So now an elliptic curve, thanks to the Riemann-Roch theorem. So this is one of the exercises that you probably give your student when you study Riemann-Roch. You can show that every single elliptic curve can be expressed by what is called a Weierstrass equation. And working into just like the projected plane. So this could be written like this. After, I assume I am in characteristic different from 2 and 3. And such an elliptic curve would be smooth as long as its discriminant locus is non-zero, and the discriminant locus take the following shape. So when delta is different from 0, you have a smooth elliptic curve. And when I give you an elliptic curve like this, one question you can ask is, what about tau? When is tau? And there is an object that you can use to relate the two. So this is called the J invariant. Then basically, you can compute it from the bit of the Weierstrass equation is like this, and the J invariant depends on time. Okay, and basically that's how you also your first description of the moduli space of the curve is based on that. You can see that's basically just a P1. There is like one point missing if you add this point, which corresponds to nodal curve. So it's typical singularity where the discriminant is 0, but F and G are not 0, would be corresponding to a singularity like this. So this would be like another curve singularity, as if you take a circle of a torus and then you shrink it. And in algebraic geometry, think of this type of singularity, have a double point singularity like this, and nodal curve they have in the J invariant, they're part of your modular space. There is also speedle curves that are kind of like much more singular. Think of a question like this one about a speedle curve, and in particular, they have F and G equal to 0, they're much more singular. So now this type of singularity are important because, as Common was mentioning, singularity are related to gauge theories. And in this particular case, there is a question. Let's assume I have an elliptic fibration. I have my discriminant locus, so clearly that locus has some point where it's 0. So what are the type of singular fiber that I get? And so this question of just understanding your codimension 1 singularity, I call them codimension 1 in the sense that think of the discriminant as a divisor. It has irreducible components, and the generic point over each irreducible component give you a certain type of fiber, singular fiber. And then what are these? So now we can come back here to Boston to answer this question. So in just after the war, Kodera, who was a Japanese student, went to a mathematician, went to the US And one of the work that he did was to classify the similarity of an elliptic surface. The case of elliptic surface is nice, two dimension, but also represent the generic situation of a component of the discriminant first. And so you have this data classification in which give actually a finite set of singularity that you see on elliptic surfaces, and some of them are just those that we have studied before. So you have the normal curve, you have the typical spindle curve, and then you have other singularities that are actually not irreducible. The first one you can think of just like remembering that if you work in P2, genus one curve is basically a cubic, and then you can think like what are the degeneration of cubic. And cubic dimension has a degree free, so it could split, for example, into a line and a conic. So when it's split into a line and a conic, you can really think of it as basically 2P1 that kind of like intersected. Okay, so this is called I2. And then the conic would also degenerate into two lines so that you can get a triangle. And so this is that I3. You can think of it really as 3P1 that form a conic. And the generalization of this type will not have like a cubic interpretation. You have to do some go-up, but type IN is basically a collection of n rational curves that intersect transversally. So now I grew up Catholic, so my mom, when she asks me what I'm doing, I tell her that I study things that like the Chapel Rosary, like in our Catholic education. So another degeneration of this would be three lines meeting at a point. So this is type 4 singularities. And then you have singularities that are a bit more exotic than that, because you won't like naturally think that they will show up. This, we could write cubic and see how these guys exist and then generalize this. So the first one that I will describe is what we call a singular fiber of type 2 star, which is like just the extreme, is essentially the one that has the extended Dynkin diagram of type 8. And so you see, you start getting this exceptional structure. E7 show up as well. 4 star will correspond to E6, and you can also get the DNC by looking at fiber of type I star N, which essentially you can see them coming from maybe a degeneration of type IN, where basically these two nodes come together and give you multiplicity 2, and then they still have ears and base. Okay, so this is your affine Dynkin diagram. So you get all of these for free. And so as a physicist, like when you look at this ADE structure showing up for free geometry, you need to ask yourself, like, is this actually related to gauge theory in one way or another? And the answer is yes. So in string theory compactification, when you have a discriminant locus that has one of these guys as the generic singular fiber, you will actually produce a gauge theory with that Lie algebra. And there are some questions about the global structure. Sometimes this fiber can actually create also non-simply there. So think of, for example, type D4. These three curves can come in such a way that when you move around your variety, they actually are rotating by something that looks like a Galois group, to the point that you can really think of them as a single curve. And then you produce an extending G2. So even this you can get. So now, as you are describing a gauge theory, typically what is the data of a gauge theory? So if when you are thinking about a gauge theory, you can start with saying, okay, I want to have a certain type of a gauge group, but you can also have the Lie algebra of the gauge group. And in F theory, this is the one that is the most accessible. It's related to the single fibers. The gauge group will involve also understanding more complex structure. But except for the Lie algebra, there is also what is called matter representation. And matter representation are just representation that show up in physics. Okay. So for example, if you study the standard model, you have the algebra of SU3 with fundamental matter. It just means you have fundamental representation. And so one question is actually where matter representation comes from. And can we understand matter representation purely mathematically, like by just the geometry of this vibration? And the answer is kind of. I'm going to explain what I mean by that. So typically, so far, think of my discriminant locus is composed of several components. And I said, for example, that if one component that has a fiber of type I3, on another component that can have a fiber of type I2. But then what happens when components collide? When components collide, I basically have what is called a collision of singularity, and it can give me something bigger. So for example, at the collision here, I might end up with a fiber of type I5. And then it's almost like some kind of chemistry of singular fibers, where you can write things like this. But the dissingularity that are over codimension 2 points, they don't necessarily are of the type classified by Kodaira. And up to now, it's an open problem in mathematics to actually identify all the type that you can get as collision in codimension 2 or collision in codimension 3. Assuming some assumption, it would be like a beautiful theorem to actually classify that much more involved than the one of Kodaira. So, however, in physics, they actually have a beautiful proposal to actually try to understand how you see matter from this. So, for example, what you have here is very much A1 plus A2 inside an A4. And if you think of it in terms of the algebra, you can ask yourself, since the gauge theory sees the adjoint representation, is it possible that if I have like some algebra G that somehow becomes much bigger into some algebra M, I can have a decomposition where I look at the adjoint of M and it becomes the adjoint of G plus something else. And so that's something else is called the characteristic representation. And this is how to identify matter, first approximation in F theory. And so this is the work of the first generation of F theorists, where they set up this algorithm. So obviously Common was involved in this. And so now, like if you look at this proposal and you think of it just from your knowledge of representation theory, you start realizing that actually it is not very well defined. The one question you will have is that, okay, so first of all, what is the meaning of this arrow? What does it mean? Like if you give me 2D algebra, you tell me that one is inside another, what does it actually mean? So it means you're thinking about an embedding. Okay, so you should consider embeddings of some D algebra inside some bigger D algebra. But then when you start thinking about the embedding of D algebra, one question would be, when do you know that two embeddings actually should be considered the same? So there is a question of equivalence, like what is the equivalence you are talking about? And why is it important? It's because if you just like take the simplest case of A1 inside A2, this is as simple as it gets. Already for this simple case, I can show you different embeddings of A1 into A2 that end up giving you different characteristic representation. And you can even visualize it. Like one of them would be basically you think about SU2, SU3, and then you take the corner of SU3 that gives you an SU2. That's one embedding. Another one is to think about rotation, and you get another one. And so clearly, in order to actually think about this decomposition of the adjoint, so we need to introduce the notion of equivalence. And so together with my collaborator, Monica Kang, who was a PhD student here at Harvard, and now she's a postdoc physics at Caltech. So we actually realized that the correct equivalence that you need here is what is called linear equivalence. And linear equivalence is about how, when you take a representation of M, it will give representation of two sub-D algebra that are basically related to each other by a natural automorphism. So with linear equivalence, there are two things that you preserve. So first of all, the characteristic representation are the same. So when you have two subalgebra that are linearly equivalent, they give the same characteristic representation, but also you preserve what is called the Dynkin index of your embedding. So the Dynkin index somehow is like the most, cheap data you can give to an embedding. So for any Lie algebra, you can define the killing form, and then you can normalize the killing form so that the longest root have length 2. So when you have an embedding like this, you can then consider what if I consider my bilinear form in G, and I compare them with the natural linear forms I have on M. And if you compare them, you see that they have to be scale of each other. And the scaling factor is a number that happens to be an integer number called the Dynkin index of the embedding. So for example, for the two possible embedding of A1, they have different Dynkin embedding. So then with Monica Kang, one thing that we did before the pandemic was actually to try to study what happens to the non-representation that show up geometrically in a theory. And to our surprise, we noticed that there is one fact that was not realized before. This is extremely cute, that all the representation that naturally show up geometrically in a theory, they all have this property that the Dynkin index is always equal to 1. And when you only have two like this, maybe it's not a big deal. But when you consider like one extreme case, I'll give you like an example that show up in theory. You consider the Lie algebra of the standard model, and you want to see how it embeds into E8, for example. And each embedding that are different can actually end up giving you different matter representation. There are actually 55 possible cases. And among the 55 possible cases, there is one that has the embedding one. And that one gives you exactly the matter that you expect from ground unified theory. And so it means that in situation where there is a little bit too much option, this principle kind of like guides you. Suppose you didn't know the geometry, usually to find the matter, we resolve singularity, then we compute intersection number of curve with divisors. They give us weight, and then we look at these weights and we identify them with given representation. This computation involving blow-ups, resolution of singularity, is extremely expensive to do. In the certain sense, like when you start doing it, you need to limit how many times you take your kids to the swimming pool, stuff like that. But all of a sudden, here, you have an extremely cheap way to actually identify the same representation. By just, you look at the possibility, and in many cases, those of Dynkin index 1 are often unique. So, yes?
With those two embeddings with the Dynkin index 1 always exist?
Yes, they do. They always exist, but not necessarily for all algebra. But for those that we study in string theory, like every single one always exists. So now let me explain where topology comes in. So we have this cube, it's not even a conjecture because you can just check it. It works in every single case. The only few cases in which it's not clear if it works involve cases where you have to mode by torsion, and there's some discrete drama that happens. So we stay away from those cases for now, and we just want to understand why something like this would be true. And so one way to understand it is first to look at the Dynkin index from the point of view of topology. So when Dynkin wrote his famous paper, I just want to do a quick statistic. Who has ever read the paper of Dynkin on classification of sub-algebra in the algebra? Nobody, right? So if you try, I just wish you good luck. It's quite an intense read. The proof, for example, that the Dynkin index is unique is the end of a long classification. And so there is a lot of notions that are introduced. Some of them now are part of our global culture in math, Dynkin diagram, and all these indices and so on. But the paper is really difficult to read. But it has a lot of treasure in it. So this is one of the old papers. If you get more familiar with it today, you have some serious advantages in the kind of new mathematics you bring. The few people, usually from Russia, who are very good at understanding these things, because there is a culture to study the algebra from a specific point of view. It's very geometrical, the Russian school. So then Dynkin wrote another paper in which he was actually trying to understand not what happens with algebra, but what happens with the groups when you have a big group embedded. And he wanted to understand, in particular, the topology, how do they compare to each other. So now, the topology of the algebra and the groups is now considered classical topic in mathematics. Take a class on it. And the first thing that you do, so first of all here, the group that I will consider, they will always be simple, simply connected. And also compact. That's when you can say the most thing. Then I will actually consider what happens when you have some group G that is inside some group M. But if you just look at one of them individually, you can say a lot of things about that. So the first work on just the topology of the groups was work by Cartan. You have beautiful paper in the 50s by people like Borel, for example. But also have beautiful result. And some of the things that you see is first H1G, H2G are typically just trivial, okay? And the first interesting thing happened when you look at the third harmonic group of G. Let's say here, let me precise over Z. You actually see that it's just described by one number. Then you can also look at the classifying space of those big groups. And so here I should mention that we also have this one called homotopy, that they are also trivial, and then P3 is related to H3. But if you look at the classifying space, so essentially there is like something called transgression. I'm not going to get into it, but they kind of relate the cohomology of the group and its classifying space with one dimension difference. And what you have is that H1, H2, and H3 of the classifying space are trivial. But H4, by transgression, is actually, you can actually write an explicit isomorphism with H3 of G. So it's also given by just integral. So now, as you see, so we have these two guys, they naturally show up in this story. And so now, like when we have a map like this, we can actually see that any map between the algebra will also induce a map between a cohomology group. But since this cohomology group are just generated by one element, everybody took, Algebra 101. If you have two groups Z, the only way you can relate them is to take the unit of one and send it to a multiple of the unit of the other. And so basically, it's like if you have G in M and you look at, you compare the cohomology, the index, like the number that we multiply is actually the Dynkin index. So in other words, you can think of the Dynkin index as characterizing the map between this big group at the level of the third cohomology group, if you look at G, or the classifying space you look at G. So now the link with Lie algebra and gauge theory is the following. So H4 of the classifying space, it's really like a classification of invariant quadratic forms. So this is what you will use to, for example, define the metric on your Lie algebra. And so these guys here are also used to classify, for example, the topological term in Wess-Zumino-Witten theories. So you classify them using H4 of BG. Whereas this one here is a classification for instantons. So when you look at a given gauge theory and you want to classify instantons, the kind of like hand-waving picture in physics would be to look at what happened at infinity. Your connection become a trivial connection, and you can compute some winding number using the Monte-Cartan form, and this gives you instanton numbers that you can classify with this group. So now, when you have an embedding that has Dynkin index 1, the property that it has is the following. It basically takes the solution of instanton of number 1 and send it to a solution of instanton number 1. So by doing that, what it means is that your instanton are stable in the sense that if it was multiplied by a Dynkin index greater than 1, you might have an instanton that was stable in one group that can be divided into 2 in the big group. So basically, the picture that we see from F theory that only the representation that we have instanton Dynkin index 1 becomes just the fact that you want to actually preserve the structure of instantons in your theory and also the structure of Wess-Zumino terms. So that's the way you can think about it. There is also an interpretation in K-theory. So typically people are familiar with the even K-theory, but there is also an odd version of K-theory. By K-1 basically represents what you will have when you study representation, and you can compute using the Chern character, you can actually compute topological value. And the third Chern character in particular gives you again the Dynkin index. So all this together, our conclusion is that the specific configuration that we see in F theory, they have Dynkin index 1, and their interpretation in gauge theory is that these are the configuration that basically preserve the unit charge for instantons, and they preserve your moduli space for Wess-Zumino terms as well. So now when I go outside of this condition here, it's more wide open like what it means. And so these are things that we are still investigating. But for example, defining Wess-Zumino-Witten theory in generalization of this is also something that is like people are still working on it. The generalization would be that this group is just going to generalize to Zn when n is basically how many components you have in G. So another thing that we are looking into is actually how the instanton decomposition actually work with that concrete example. Like for the few models that we know that don't have an elliptic vibration that give representation that are not Dynkin index 1, like can we actually see anything in the geometry that will have some interpretation of some instanton that are badly behaving? So that's what it is. So I'm going to stop here for today.